Alright, so I'm here at the Golden Gate Bridge, and as you can see, it's kind of going behind the clouds there. But yeah, so today we're going to talk about suspension bridges. So at the Golden Gate Bridge, there are many different models and displays to look at and play around with. And first up, we're going to investigate how the height of the main supports of the bridge affects the tension in the cables. So each of these decks are weighing the same, but because you can see these heights are much different. This one is really hard, this one is a bit easier, and this one is by far the easiest and loosest. Alright, so let's take a closer look at why this is. When we have the tension in the cable of the bridge, we can represent this by a vector or just an arrow. And this arrow will be going out at a certain angle depending on how the cable meets the bridge. And this arrow can be broken down into its components. So we have our vertical and our horizontal component. The vertical component is the amount of the tension that is acting up and down, and the horizontal component is the part of the tension that is acting left and right. And you can use a bit of trigonometry to find these, but what we're more interested in is using the components to find the overall tension in the cable, and that would be done by using Pythagorean theorem. So the square of each of the components summed together equals the square of the total tension in the cable, but we'll come back to that in a second. So if we take two bridges that are both supporting the same deck, but they have two different heights for their supports, we can take a look at the tension in the cables, and we can break it down into the vertical and horizontal components. And what we'll see is that the vertical component is going to be the same for both bridges because they are both supporting the same mass, the same force of gravity downwards is acting upon both bridges. So the vertical component will be the same. But now the angle at which the rope is, or the cable is coming in at, is different, and we're going to have a different horizontal component of that tension. And that horizontal component contributes to a lower overall tension in the higher bridge support than the lower bridge support. And what this means is, when we have higher supports, the tension is less, so the cables don't need to be as strong, and we can get the materials cheaper. But the trade-off here is that the higher supports will cost extra. So engineers designing suspension bridges have to do a mathematical analysis to determine what is the optimal bridge height to minimize the cost. Most suspension bridges are made by taking small deck sections and chaining them together, like shown in this model. All bridges have to deal with wind pushing against them, and the Golden Gate Bridge, being in San Francisco, also has to deal with this because it's very windy there. And also, it has the added challenge of being in an earthquake area. So it has to be very flexible and move with the wind and the earthquakes. And the Golden Gate Bridge is designed to move up to 8.4 meters or around 27 feet with strong winds, which is pretty amazing how they get it to be that flexible. On December 1st, 1951, a storm caused enough bending and vibration on the bridge to cause some minor damage. So, from 1953 to 1954, the deck was retrofitted to increase its strength. So let's head back and check that out. Okay, so over here we can see the original shape of the bridge deck and the retrofitted deck, in which they added this bit on the bottom, adding a lot of strength. You can see the comparison. This is much harder to move. So we're here under the Golden Gate Bridge, and it's actually pretty windy and noisy because the car's going above us. But you can actually see back here the suspension deck that we were talking about before in that little model. So I'm here in front of one of the cables, a cross section of the cable, and you can just see how huge this is. It's almost a meter in diameter. actually look up close, it's actually made up of over 27,000 smaller wires. This is pretty amazing. So these cables would have been too heavy to bring over on barges and hoist up to the main supports of the bridge. So what the engineers did was they came up with an innovative solution where they took all the 27,000 cables and spun them on site, so they didn't have to bring them over. And so these 27,000 cables, had they been put end to end, they would have been 80,000 miles long. And that's more than enough to go around the Earth 3 times with 5,000 miles to spare. Alright, so that's all for this video, guys. Thanks for watching, and I'll see you next time.